We have arrived at section 5.4, where we're going to talk about two properties that linear maps may or may not possess. So the first one is the notion of being one-to-one. And the framing here is that we have a linear map, L, that maps some vector space V to another vector space, W. And now we say that L is one-to-one if L of U equal to L of V implies that U is equal to V. So in other words, what this means is that for every point in the target space, W, there's precisely one point in the source space that maps U there. So in other words, if we have the source space V and then we have W here, then for every point L of U in the range, there's precisely one. There's only one point that maps there. So this would be one-to-one. So the opposite of that would be if you have a situation where you have two different points that both map to the same. So if L of U is equal to L of V for two different vectors V, then this would be a map that is not one-to-one. So another way of expressing this would be to say, you could have used so an alternative definition here would be to use the converse, which is to say that if U is not equal to V, then L of U is not equal to L of V. These two statements are logically equivalent, so you could use one or the other. Another name for this property is injective. So the other property we're going to talk about is the property of being onto. So this is quite simple. It simply means that every vector in the target space W is the image of something. So in other words, let's draw a picture. So if so we have the source space V, we have the target space W, and then if you map all the points in V through this mapping L, then every piece of W is going to be hit. So everything here, there are no gaps, basically. So this is when something is onto, and not onto would be that you have some regions, or at least one point to be precise, in the target space that's not hit. So say there's some area that we don't hit. So the problem is this little region up in the corner. And for an alternative definition, so make sure you think this through so that you understand that these are equivalent. So onto means that for every vector W in the target space, there exists a vector V in the source space such that W is the image of V. And the fancy word for this property is surjective. So we're not really going to use these Latin words. We're going to say one-to-one and onto for the most part. But you might see the other ones from time to time, so they're good to recognize. So let's do a few examples to illustrate what these properties mean. So let's take as our source space P3, the set of all polynomials that are cubic or less, and our target space is the space of all quadratic polynomials or less, and our map is differentiation. So if you have some polynomial then this maps to okay, so this is a guy in P3, and this is in P2. So this is how the map works. It takes a cubic polynomial as input, and it gives you a quadratic polynomial as its output. Now, you can easily convince yourself that this is not a one-to-one map. And the reason is that it maps the constants to 0 as well as 0. So if we take the 0 polynomial, then this maps to the point 0, but also any constant polynomial maps to 0. And since 0 and 1 are two different vectors in P3, and they both map to the same point 0, this is not a one-to-one map. However, L is onto. So for every W in W, there exists V such that V prime is equal to W. Specifically, so V is the polynomial AX plus 1/2 BX squared plus 1/3 CX cubed. So in other words, you can go back. So the pre-image is integration in this case. So this map is it's one-to-one. It's not one-to-one, but it is onto. But an important thing to know about linear maps and general vector spaces is that these properties are not connected, right? So here it satisfies one and it doesn't satisfy the other. And the other thing that's important to know is that they depend crucially on what your spaces are. They depend not only on the map itself, but also on the spaces. Because if I just change the target space to P3, and we still have L as differentiation, then L is still not on one-to-one. Let's shorten that to one-to-one. And in this case, it's not onto either. And why is that? Because if you take a cubic polynomial and you differentiate it, then you get a polynomial of degree at most 2. So any cubic term cannot be the target of anything. So to formalize that, consider, say, x cubed. Then this is something that does belong to P3, but there is no P, there's no cubic polynomial such that its derivative is equal to q. You would need a fourth order polynomial, and that's outside of our source space. And these properties, they also make sense on infinite dimensional spaces. So if we take V and W to both be the spaces of all polynomials, we still have differentiation, then L is not one-to-one, precisely because, for instance, the constant polynomial p equal to 1 maps to 0, as well as the 0 polynomial maps to 0. So the counterexample is the same in all cases here. But in this case, L is onto. If Q is some then if we set P to be some Ci xi plus 1, so we integrate, then P prime is equal to Q. So, right. So it's the same as the first example, I suppose. L is not one-to-one, but it is onto in this case. So next, let's consider our archetypical example in this course. which is the matrix vector multiplication. So we'll set V to be Rn, we set W to be Rm, and we take L of x to be Ax for some m by n matrix A. Alright, so now what does onto mean? So L is onto. This means that for every y in Rm, there exists x in Rn such that Ax is equal to y. So when does this happen? So this happens when you have a pivot in if you compute the RAF of A, then you cannot have any zero rows. So you must have a pivot in every row of the RAF of A. In that case, the system is always consistent. So in this case, that happens when the rank of A is equal to m. So in other words, there is a pivot in every row of the RREF of A. In this case, it's impossible for this linear system Ax equal to y to be inconsistent. For every y, it has a solution. So now when is L 1 to 1? If Ax equal to Ay implies x is equal to y. So now observe that Ax equal to Ay, this is the same as solving the system Ax minus y is equal to 0. And that has the trivial solution if and only if you have one pivot in every column of the RAF of A, which is to say that the rank of A equals to the number of columns, which is n. So Ax minus y equal to 0 has only the trivial solution when rank of A is equal to n. In other words, there is a pivot in every column of the RREF of A. All right, so let's highlight this. So L is onto if and only if the rank is equal to m, and L is 1 to 1 if and only if the rank is equal to n. So notice in particular that if the matrix is square, then A is onto if and only if it's 1 to 1. So particular case, which is A is square. Let me phrase that. Suppose A is square. So that m is equal to n. Then in this particular case, you have A is 1 to 1 if and only if A is onto. But notice that this holds only for square matrices. It is not generally the case. So to look at some examples, if we take, say you have the matrix, so L maps R2, to R3, then A is 1 to 1. So in this case, the rank of A is equal to 2. The matrix itself is in its REF, so we can immediately read off the rank. There are 2 pivots. So A is 1 to 1, since rank of A is equal to number of columns. But A is not on 2, since the rank of A is less than the number of rows. So in particular, if Y is, say, 0, 0, 1, then AX equal to Y has no solution. So this vector Y is not the target of any vector X. No matter what vector X you choose, 8 times X is never equal to that Y. And of course, if I just flip A over and take its transpose, so here was one example. Let's do another one. So L in this case maps R3 to R2, then A is on 2. Since the rank of A is equal to 2 is equal to the number of rows. So you see, if for any Y, so if you want to be explicit here, if you take any vector Y, that's Y1, Y2, and R2, we have the case that Y is equal to AX for X equal to Y1, Y2, 0, for instance. All right, so every vector Y, every vector Y is the target of some vector X. However, A is not 1 to 1. So in order to see this, we can set U equal to 0 and V as 0, 0, 1. Then U is certainly not equal to V, but LU is equal to LV is the 0 vector. So next we'll prove 2 simple theorems that characterize when a linear map is 1 to 1 or on 2. So let L from V to W be a linear map. For V and W vector spaces, of course, I won't write it out. Then L is 1 to 1 if and only if its kernel consists only of the 0 vector, of the trivial kernel. So remember, 0 is always in the kernel, in the null space, but sometimes there are other vectors as well. Let's prove this. This is extraordinarily simple. So let's go in this direction first. Suppose L is 1 to 1. Now clearly L of 0 is equal to 0. And since L is 1 to 1, x not equal to 0 implies L of x is not equal to 0. So we say that the kernel of L consists only of the 0 vector. Right, we see this, right? So 0 always belongs in the kernel, and the fact that it's 1 to 1 tells you precisely that there is no other vector other than 0 that also maps to the 0 vector. Now let's go in the other direction. Suppose the kernel of L is equal to just the zero vector, then suppose also that Lx is equal to Ly. We need to prove that x is equal to y. And that equation is the same as saying that L of x minus y is equal to 0. These two are the same. And now, since the null space of L is 0, this means that x is minus y is equal to 0. So here we use the assumption that the only vector that maps to 0 is 0. So since L of x minus y is equal to 0, we must have x minus y is equal to 0, which of course is to say x is equal to y. So that establishes that L is 1 to 1. So now the other theorem says something about when L is onto. So as usual, L maps V to W. So let this be a linear map. Where W is finite dimensional. Then in that case we have the claim that L is onto if and only if the dimension of the range is equal to the dimension of W. Proof is again very simple. So in this direction, we also suppose then by definition range L is equal to W, so obviously their dimensions must be the same as well. If, this is pure triviality. If range of L is equal to W, then of course their dimensions have to be the same as well. And the other direction is really not particularly much harder. Suppose the dimensions agree. Then we know as I said, W prime to be the range of L. This is a subspace of W, because we proved that in the previous section, that the range is always a subspace. And we also know that the dimension of W prime is equal to the dimension of W. And then we had a theorem in a previous section that says that the only subspace that has the same dimension as the ambient space is the ambient space itself. So in this case, W is equal to W. W prime is equal to W, which is precisely to say that L is onto. So now these two theorems, if you combine them, then something interesting happens in the case when the dimensions of V and W are the same. So let's see how this works. So let's state a new theorem. So as usual, let L be a linear map from two vector spaces V between two vector spaces V and W. And now we suppose that the dimension of V is equal to the dimension of W. And of course these have to be finite. Then in this case, L is onto if and only if L is 1 to 1. So notice that earlier on in this lecture we made a big point about how these properties are uncorrelated, that a map can be 1 to 1 without being onto and the other way around. Well, let's go back and look at them. So here were our two prime examples for matrices. So in this case, the main point here is that this matrix is rectangular. So the dimension of the target space is larger than the dimension of the source space, and then here we have the other way around. And the same thing if we can find our polynomials. So over here, you notice in this example, what makes it possible for a map in this case to be onto but not 1 to 1 is precisely that the dimension of the source space is different than the dimension of the target space. So let's prove this theorem. So let n be defined as the dimension of V. This is also equal to the dimension of W. Then the dimension theorem from previous lecture states that the dimension of the kernel of L plus the dimension of the range of L is equal to n. So they add up to the dimension of the source space. Now L is onto, according to the theorem on the previous slide, this happens if the dimension of the range of L is equal to n. And this happens if and only if so if this guy is equal to n, then, and so if we call this equality star, so here I'm going to use the dimension theorem. So if the dimension of the range of L is n, then it follows that the dimension of the kernel has to be 0. So using the dimension theorem, we see that the dimension of the range is n if and only if the dimension of the kernel is 0, and the only linear space that has dimension 0 is, and the only space that has dimension 0 is the trivial space, and that's to say that L is 1 to 1. So next we're going to state another theorem. Framing is the same. Every theorem in this section pretty much has the same framing. You have a linear map. Sometimes we need to assume that the spaces are finite dimensional. For this particular one we don't. Then we have the following statements. So first of all, if L is 1 to 1, and S is a linearly independent set, then L of S is a linearly independent set in W. So in other words, if you have a map that's 1 to 1, then it maps linearly independent sets to linearly independent sets. So what do onto maps do? Well, if L is onto, well, they map spanning sets to spanning sets. So if L is onto and S is a spanning set, in V, then L of S is a spanning set in W. Let's prove this. So suppose that L is 1 to 1, and that S is linearly independent. Rewrite a little smaller, and that S alright, then we'll set Wi to be L of Ui, and we need to prove that the set of Wi's is a linearly independent set. So suppose some Ci Wi is equal to 0. This is the same, just using the definition of Wi, this is the same as saying that the sum of Ci times Lui is 0, and then by linearity I can move the L to the outside. So the first one here is just definition of the Wi, and here I use linearity. And now since L is 1 to 1, this last statement is equivalent to that being 0, so here I use L is 1 to 1, so it has only the trivial kernel, so the only vector that L maps to 0 is the 0 vector, so the argument here of L must be 0. And now there's only one step left, so the only assumption we haven't used yet is that Ui is a linearly independent set, and that's what we'll use in the final step here. So here we use that Ui is linearly independent to show that the only linear combination of the Ui's that adds up to 0 is the trivial one where all the Ci's are 0. So this proves that Wi is linearly independent. So next we're going to prove B. I'm going to delete all this stuff, so let me linger for just a few seconds in case somebody wants to pause and look over this proof. Alright, now we'll delete it. And next we'll prove part B. So suppose L is onto and that S is a spanning set. And set Wi to be L of ui for all I. And we need to prove that the set of all wi is a spanning set. And this is pretty straightforward. If we pick W in the target space, we need to build a V in the source space that maps onto W. So now we just use one of our assumptions at a time. So since L is onto, I know that there exists a V in the source space such that LV is equal to W. And since the UIs form a spanning set, I know that there exists CI such that V is equal to some CI VI. Now, or then, L of V is L of some CI VI, some CI L of VI, some CI WI, and now we've precisely proven what we needed to prove. We needed to build, okay, so this was W, maybe we should have written this out. So W is L of V, and we show that W can be written as a linear combination of the WIs. So WI, the set of WIs, is a spanning set. And of course, this was equal to L of S. Right. And that's it.